Welcome to lecture 9 on module 1 of computer organization, in which we will be discussing about instructions and instruction sequencing along with the register transfer notation, assembly language notations, as well as the straight line sequencing and the branching along with the conditional codes. In this slide, we will look into the instructions and instruction sequencing. So this computer program has to perform many functions that should be in a sequence of small steps, such as adding two numbers, testing for a particular condition, reading character from a keyboard, sending the character to be displayed on the screen, and so on. So the computer must have the instructions capable of performing all these operations. Typically, there are four such operations, that is data transfer between the memory and the processor registers, arithmetic and logical operations on data, program sequencing and control, and IO transfers. The data transfer from memory and the processor register is because the programs as well as data are stored in the memory. Arithmetic and logic operations has to be performed because if you want to perform any arithmetic operations or logic operations, there should be the data has to be transferred to the ALU unit. The ALU unit has to perform the corresponding task. Program sequencing and the control, this is particularly used when there are some loop statements or the branching of instructions. Whenever there is a branching, then program sequencing is required. IO transfers, whenever you want to transfer a data from a processor into an external device, then you need to have input output transfers, or if you want to give the input to the device through a mic, or you want to take a photograph, then all these are the IO transfers. So this computer system has to perform all these above tasks. In this particular slide, we will look into the register transfer notation. We know that the computer performs various tasks, and these tasks are in the form of steps, and these steps are in the form of instructions. Whenever an system executes certain instruction or performs some task, there is instructions that have the source register as well as the destination, or the source location as well as the destination location. Therefore, a lot of information transfer takes place between one location and the other location. The location may be a memory locations, it may be a processor registers, or the transfer may take place between the registers and the IO subsystem. In all these cases, there should be a specific way to represent the transfer of registers or the transfer of information between the memory locations. In this particular example, the square bracket on location, if you write location with the square bracket, that means that location will have one address. The content that is present in that address is copied to the register R1. So in case of example 2, R3, R1 plus R2. In this case, you will have two registers, R1 and R2. These two registers will have some data. You will add these two, and the resultant value is stored into R3. This notation represents add two numbers and store the result in the R3 register. This type of instructions are called as the register transfer notation, or RTN. Always the right hand side of the equation represents the value, whereas the left hand side represents the location where the result has to be stored. Location to store the result. Location to store the result. In this particular slide, we will be discussing about the assembly language notation. However, in our previous lectures, we had discussed that there are different types of programming language, like the machine language programming, assembly language programming, and high level language programming. So in case of assembly language program, you will have a specific notations. For example, in this particular example, you have an instruction move location comma R1. Here you can term it as a mnemonic and it will have operands. Mnemonic represents what the action is, what the action has to be done. For example, in the second example you have the add. In case of first you have move. Move indicates that the content in location has to be copied to the register R1. Here you can write it as mnemonic. This is the operand, source operand. This is the destination operand. Now the content that is present in the source operand will be moved to the content that is into the destination operand. Here the content of location LOC, this particular value will not change, whereas the content of R1 will be overwritten. Similarly, in the second example, add R1, R2, R3. Here what happens is, the processor registers, we have two registers R1 and R2. We need to add these two numbers. The resulting sum is stored in R3. That is R1 plus R2. The resulting sum is stored in R3. This is what this particular instruction represents. This type of notation is called as assembly language notation. This is there are many different types of assembly language notations that we will discuss in the second module. Adding two number is a very fundamental capability in case of any computers. For that matter, it may be a microcontroller or a microprocessor. Addition of two numbers is a very basic problem. Here, in this case, it is represented as C equal to A plus B. Here the C will be the destination register. These are the source operands. These are the source operands. So here, in case of high level language, we can represent it as C with the content of, if you add the content of A and B, A is one register, A is one location and B is one location. The content of A and B are added and it is assigned to the destination location C. The destination location C. Here destination is C. These are also called as the operands. Destination operand, these two are the source operands. Source operands. Based on the number of operands in any of the instructions, it can be categorized into a 3 address instruction, 2 address instruction and the single address instruction. In case of 3 address instruction, you will have the 3 address of source, 2 source and 1 destination. For example, if you want to perform the task of adding 3 numbers that are present in 3 different locations, then you can write it as add A comma B comma C. In this case, C will be considered as the destination register and sum of A, B and C will be loaded into the C register. In this case, what happens is the content of C gets erased. The original content of C register gets erased and it will be replaced by the sum of A, B and C. The contents that are present in A, B and C will be summed together and copied back to the C register. Similarly, in case of two address instruction, you will have only two address, that is one for source and one for destination. So here the operation can be, let us assume we have to perform an addition of two numbers. Here you will have one, A will be the source and B will be the destination. The sum of A and B will be copied to the B register. Even here the content of B register gets erased. Next, however, the data that is present, the sum is present in B. If you want to copy it to C, then you need to use the instruction move B comma C. In this case, B is the source and C is the destination. The content of B is copied to C register. In case of single address instruction, for example, if you want to perform the addition of two numbers using single address instruction, you can use the instruction such as add B. Now in this case, the content of B is added with accumulator and the destination will be accumulator itself. Now if you use the instruction add B, the content of accumulator is added with the content of B register and the sum is copied back to the accumulator. Similarly, you can have the instruction add A, where the content of accumulator gets added by itself and the result is stored back into the accumulator. This is how the single address instruction works. Now if there is a 3 address instruction, why do we need to have a 2 address instruction? What happens is, when you perform the addition of 3 address instructions, in each source and destination will have the address. It will be difficult to execute these using a single instruction. In such cases, it is better to have an optimized instruction which can be performed using a single instruction. That is the main purpose of having 2 address instruction and single address instruction. In order to optimize the code and also to maximize the speed, we will split the 3 address instruction into 2 address instruction or single address instruction based on the requirement, and most of the times this can be done by the compiler in case of higher level language. In case of assembly language program, the programmer has to be wise enough to choose the address or the instructions so that the code is optimized, which avoids unnecessary delay in the execution of the program. However, in order to execute any instruction, there should be a transfer of data from memory to the processor and from processor to the memory. In order to perform this transfer of instructions or data from memory to processor or from processor to memory, we have 2 sophisticated instructions like load and store. If you have the instruction load A, here the A specifies the address of memory location. Now when you use the instruction load A, the content that is present in the memory location A is copied to the accumulator, whereas the store instruction stores the content of accumulator back into the memory location A. If we take the example of C is the destination register, the sum of A and B, sum of the contents of A and B is copied to C. Now what has to be done is, you need to load the value into accumulator and add it with the B, then you need to store it back. Here actually you need to use the instruction load A and load B. After that you need to add the instruction. Now when you use the instruction load A, what happens is, the content that is present in memory location A is copied to accumulator. When you use add B, it will add the content that is present in accumulator with the content of B register, and the result is stored back into the accumulator. It will add the content that is present in accumulator with the B register and store the result back into the accumulator. When you use this instruction store C, what happens is the content that is present in the accumulator will be copied to the the address pointed by the C register. C is the address now. In this address, the content that is present in accumulator will be copied. This is how the load and store instruction work. The general purpose registers are the temporary storage registers that are available in the CPU. In most of the modern computers, there are 8 to 32 different types of registers. These registers are much faster in transferring the data as compared to the memory locations. What happens is the most frequently used data is stored in these registers that are used for further processing. Let this Ri represents the registers. Ri represent the general purpose register. So in this case, load A, Ri, what happens is the content that is present in the location A is copied to Ri. Here Ri, the register Ri is the destination register. And Ri represents the number. If there are 8 registers, then this I ranges from 0 to 8. 0 to, if there are 8 registers, it represents from 0 to 7. Similarly, store Ri, A, the content that is present in Ri is copied to the location A. Add A, Ri, this adds the content of A with the content of Ri, and the result is stored in Ri. This register behaves as an accumulator. You can perform any task and you can store the data in register temporarily for further processing. Till now we had discussed about the load and store instructions that are used to transfer the data from the memory into the processor or from processor to the memory. We have an alternate instruction that performs the same task as the load and store instruction, that is move. What this move instruction does is, it is nothing but the copy the content that is present in the source to the destination. This move instruction just performs the task same as the copy. It copies the content from the source. It copies the content from the source into destination. So what happens is, in both the source and destination, the results will be same. The copy of the source is copied into the destination. So for example, if you compare the instruction load A, Ri, we know that what this load A, Ri does. It loads the content that is present in the location A into Ri. The same task is performed by the move instruction as move A, Ri. It copies the content that is present in A to Ri. Similarly, if you have an instruction store Ri, A, the same task can be performed using the move instruction move Ri, A. The content of Ri is copied to A. When the data are moved to and from the processor, the move instruction can be used rather than the load or the store instructions. In case of load and store instructions, the copy however the copying of data or the transfer of data takes place, but it also takes a larger machine cycle as compared to the move instruction. So for example, if we have an instruction or a task C equal to A plus B, then it can be performed using move A comma Ri, add B comma Ri, and move the content, that is sum to C register. That is what C equal to A plus B. The same task can be performed using the load and store instructions. We have already seen that it can be this load and store instruction can be replaced by move instructions as shown here. In this particular slide, we will look into the instruction execution and straight line sequencing. In order to understand this concept, well, let us take the task same as the previous slide, that is C equal to A plus B. Let us assume the word length of it to be 32-bit. So in order to represent this task using the assembly language program, we can represent it using the three instructions, that is move A comma R0, move A comma R0, add B comma R0, and move R0 comma C. As simple as this. Load the content of A to one register, add the content of B with the register, then move the sum back into the C register. This is what the instruction does. So let us assume each instruction takes a 32 bits wide. Each instruction takes a 32 bit wide, and the successive word locations are occupied by individual instructions. That means we know that this, as soon as you write the instruction move A comma R0, the same move A comma R0 will not sit into the memory. Instead, it will be converted into the assembly language program. What we have, assembly language will be converted into a machine language, and the machine language is nothing but the representation in the form of ones and zeros. The entire program is represented in the form of ones and zeros, and this sequence of binary numbers are stored in this location. That sequence corresponds to the instruction move A comma R0. So here, that is called assembling. After assembling, you will get a binary code. The binary code will be loaded into a memory. During the execution phase, the code that is present in the memory location 1. So here, this is the starting address. I is the starting address. So we know that we are already discussed about how the execution takes place, what is the program counter, what is the instruction register, and all those things. Here, as soon as the execution starts, the content, that is the address that is present in I, will be loaded into the program counter, that is PC, and the execution starts. Once the PC is loaded, this particular instruction will be handed over to the CPU through a particular process. We have already discussed that. And there is a three process, that is fetch, decode, and execute. Fetch from the memory, the code that is present in ith location will be fetched. It will be decoded in the sense the processor has to understand what it is. Here it is move. That means as soon as this instruction is decoded, the processor understands that a copy of the content that is present in A has to be moved to R0 register. As soon as the execution takes place, the content of that the copy of A is copied into R0. Once it is done, once the execution is complete, the PC value will be incremented by 1, or in this case, since it is the word length is 32-bit, it will be incremented by 4. That is, the next instruction will be present in the location I plus 4. So the next instruction that has to be fetched is from the location PC equal to I plus 4, that is add B comma R0. Even here the same process continues. The fetch, decode, and execute phase will continue. And here during add, what it does is it will add the content of R0 with the B register, and next the move R0 comma C, that is the value that is present in R0, the sum that is present in R0 will be copied to C register. This is how the task C equal to A plus B is executed. This process of executing the instructions in a sequential word order one after the other is called as straight line sequencing. Branching is a type of program which deviates from the main program and executes a specific set of code that are required based on the conditions. So typically in case of branching we have two types. One is conditional branching and unconditional branching. In case of conditional branching, the branching or the location is transferred or the execution is transferred to other location based on a particular condition, whereas in case of unconditional, without any particular condition, the control is passed to the label that is mentioned in the program. In this particular slide we will look into the two figures. In one case there is no branching and the other case with branching. So suppose let us assume that we need to perform a task to add n numbers. The one simple approach is to keep on adding all the n numbers as mentioned in the first figure. That is move number 1 comma r0, add num2 comma r0, add num3, num4, num5, num6, num n. If there are 100 numbers, you keep on writing this particular instruction 100 times. After adding 100 numbers, then move the result, that is R0, into a particular register sum. This is simple method. Even though it is simple method, but the complexity of the program as well as the length of the program will drastically increase, which not only drains out the limited memory resources that are present in the processor, but also adds up to the complexity of the program. Whereas in case of branching, this program, if you want to add the 100 numbers, you can represent the same code using branching with less than 10 number of lines. See here in this particular example, you need to move the count to one particular register. What is the number of what is the count of number you need to add? For example, if you want to add 100 numbers, move that 100 to R1 register. This R1 register behaves as a counter. Next you need to clear R0. You take one particular register, then add two numbers, add R1 and R0, or you keep on adding R0 with itself. Let us take adding R0. Next, what you need to do is you need to decrement the count. Once one number you have added, decrement the count, decrease the count. If there is 100 numbers to be added, in the one after adding one number, then it should get reduced to 99. That will be done by the instruction decrement R1. Now after execution of this, the number becomes 99. In this case, you have, I said that there is a conditional as well as unconditional. This is the conditional branch instruction, where the branch will check for the condition whether it is greater than 0. In this case, it will check whether whether the count is greater than 0. Yes, it is 99, it is greater than 0. So it loops up, it jumps back to the label mentioned. Here the label mentioned is loop, it jumps back here. Here again it will add one more number, add R0. The next number will be added to the previous result. So it keeps on adding, and when the next number is added, the next instruction is decrement R1. The R1 becomes 98, and again it is greater than 0, and this process keeps on repeating until R1 becomes 0. When R1 becomes 0, the conditional, this branch greater than 0, this condition becomes false. It comes out of loop, and this result that is present in R0 is moved into some location, a memory location, which is meant to store the result. The See, by analyzing these two instructions, if the 100 lines of code can be reduced to less than 10 lines of code using the branching instruction. This is how the memory is conserved or memory is preserved, as well as the complexity of the program can be reduced using the branching instructions. We know that from our previous discussion that the processor is capable of performing various tasks such as performing arithmetic operations as well as the logical operations. Whenever a processor performs the logical as well as arithmetic operations, it has to keep the track of information about the result of various operations. In such cases, what happens is, after performing certain tasks, the result may be negative, the result may be zero, the result cannot be represented in a specific word length, or there may be a carry beyond the word length, or there may be a bit that has to be represented that is beyond your word length. All these has to be represented using a particular status flag. So this status flag is also called as condition code flags. So there is all these negative, zero, overflow and carry bits are grouped together to form a status register. This status register gives the status of operations that is carried out by the processor. So if the negative flag in the status bit is set to 1, then the result of the operation is negative. Whereas if the result is 0, after performing certain task, if the result is 0 or the status 0 bit in the status flag is set to 1, then that indicates the result is 0. Similarly, there may be a state during which the range of result is more than the range that can be represented by a destination operand. In such cases, the condition is called as the overflow flag. For example, if you have a 8-bit number or an operand which is of 8-bit, if the result is of 10-bit, if the result is of 10-bit, it cannot be represented using 8-bit destination register. 8-bit destination register cannot hold the 10-bit result. Such condition is represented in the status register by setting the overflow flag. Similarly, if there is a carry from the MSB bit, if for example if you have a 8-bit result and you have a 8-bit destination register, and what happens is there is a carry from the most significant bit. Let us assume this is the 7th bit, starts from 0, total 8 bits. So if there is a carry out from the 7th bit to the 8th bit, or from the carry out from the MSB most significant bit, if I say that it is 7th bit, don't be confused that if you represent 8-bit, the locations are 0 to 7, then 8. If there is a carry from 7th position to 8th position, then it can be indicated by setting the carry flag in the status register. This type of conditions are indicated by the carry bit. By this, we have come to an end of module 1, which comprises of 9 lecture videos comprising the entire topic covered or the entire syllabus